Okay. Morning, everyone. So let's get started. So first of all, just to let everyone know, like I actually mentioned that quite a few times before, our final exam will be online from 8 to 10 a.m. I believe it's December 15th, right? Anyway, yeah, please check out the website and we'll release the notice today. And then from then on, we probably will send out this reminder every 2 days to make sure everyone not gonna skip the final exam. Yeah, because I know a few students will be traveling and even out of states, right? So doing the online exam, I guess, is a most convenient way for everyone. You don't need to get up very early and arrive here at 8 a.m. in a cold winter morning, right? And so, and today is the second last lecture. So on Thursday, we'll give a quick review of what we have discussed throughout the semester and give you a hint about how to prepare the final exam. But you don't need to worry too much about the final exam because we do need some final exam. That's the reason we use final exam, right? So we won't ask you to calculate anything, prove anything with mathematical languages. That's very inconvenient in Canvas, right? So what we want is just to check your basic understanding about the concepts and algorithm we have discussed previously. So if you can spend some time like walking through our slides and make sure you understand the content of slides, you'll be fine for the final exam. Okay, and also we have we still have the homework due for homework 5, I guess, right, for the neural network, and also final project report. Especially for a final project report, please make sure to submit the final project report in time because we are tight in the we're tight about the deadline to give the final grade, right? The registrar office won't allow us to extend, so please do not ask for some extension for final project report. Okay, any other question regarding our schedule? Perfect. So today we're going to talk about another instance of probabilistic learning or Bayesian learning, which is called naive Bayes classifier. As we'll see later, you can view it as a generative model in that we actually define a probabilistic or Bayesian model about how we're going to generate the labels and the input features. It's different from logistic regression where you're not modeling how the features are generated. You're modeling the conditional model. Right? You're modeling conditional on the feature vector. What's the probability you're going to give a positive prediction or negative prediction, right? So we're going to introduce the definition of or formulation of naive Bayes classifier, and then we're going to talk about an efficient way of learning naive Bayes classifier. So first, what is naive Bayes classifier? And later we'll talk about, first we're going to talk about what is Bayes classifier, right? And then why we call it naive Bayes classifier. Naive means that you're going to make some kind of simplification, right? We're gonna explain actually doing some naive modeling is necessary because if you're doing super smart Bayes classifier, you will have to face the exponential growth of the parameters, which you will not be able to handle in practice, right? So you have to make your model more stupid so that it will be feasible for you to train model. Okay, so what's the idea, right? What's the idea? The idea is that in this model, right, in this Bayes model, we're not only modeling the label given the example, given the training input X, right? We're trying to model the joint probability distribution over both the input feature vector and the label. So that's the key idea. So it's the whole generative model, meaning that, okay, I'm going to model in both feature and the label. So once we have such a model, right, during the prediction, right, we're assuming that, okay, we have given an input feature vector X, right? Then we want to use this joint probability model to give us the conditional probability. That is, given your feature vector X, what is the probability that your label is 1 or -1, right? And how can we do this? We can use the so-called Bayes rule, right? So according to the Bayes rule, this conditional probability, or sometimes we often, we often call it posterior probability, right? Posterior probability of the label being Y given this input X, right? According to Bayes rule, we can write it as dividing this joint probability by the marginal probability of X, right? Of the feature vector X. And this joint probability can be further decomposed as the marginal probability that your label takes small y, right? And then what is the probability, or what is the likelihood of your feature vector is X given your specific label small y, right? So this is just a straightforward application of Bayes rule. Any question at this point? Okay. And then, in practice, we're gonna, once we have such kind of probability, right? We got this posterior probability that we can measure the chance that given X, your label is 1 or -1, right? Or even class 2, class 3, right? If you're doing multi-class prediction, right? We need to make a decision, right? How can we make a decision? Which label is our final prediction? Any thought? Right, we have the posterior probability for your label being 1, 2, 3, 4, right? And now you want to make a decision, right? You want to decide what's your label you're gonna predict. How you're gonna decide? Yeah, but you got, for example, you're predicting, you possibly have 4 classes to predict, right? You have 4 possible labels, right? You got the posterior probability of taking each label. Now you want to pick up one as your final prediction. Which one are you gonna? The highest one, right? So that means in practice, you want to decide your final prediction. You're gonna pick up the label who has the biggest posterior probability, right? Right, that's our general framework. Any questions so far? Right. Okay. So now let us look at our prediction rule, right? Our prediction rule, which is to maximize the posterior probability of a label given the training, given the input feature vector X, right? We know that according to Bayes rule, the denominator, which is the marginal probability of your feature vector, actually is constant to the label Y, right? So when you do the maximization, you can ignore it. So our maximization essentially is to maximize the product of the prior of being a particular label, and the likelihood of observing this particular feature vector X given the label, right? So we see the some form like map estimation again, right? We're trying to maximize the product of the prior and the likelihood. But now the prior refers to the prior probability of a particular label. And the likelihood is referred to as the likelihood of the feature vector given the particular label, right? And we want to train such a model, right? Meaning that we need to specify how we're going to model the prior and how we're going to model the likelihood of the feature vector given the label. Right? That's what our naive Bayes classifiers are going to do. Right? Meaning that we need these two sets of probabilities. Right? So now let us through a concrete example, say how we're going to model these two sets of probabilities, the prior of the labels and the likelihood of the feature vector given a particular label. Right? So any question before we dive into the details? No, I don't know. Yeah, so we here we just give a general framework, right? So we see that, okay, the goal of our model is that we want to specify a joint distribution over both the label and the feature vectors, right? And then during our prediction, what we need to essentially is to maximize this joint probability. Right? This joint probability is decomposed as the prior of the label, multiplying, given the label, what is the likelihood of X, right? So that's our framework. Then to specify or to instantiate our model, right? We need to design what's the model for the prior, what's the model for the likelihood. But before that, I want to make sure that everyone feels comfortable about this framework. Right? Then we're going to talk about in detail how we're going to specify prior modeling and likelihood model. Everyone's comfortable? Great. So we're going to go back to our tennis example, right? When we talk about decision trees, right? We use that to construct some example to run our decision tree, right? Now we're going to reuse this example, right? So suppose from the tennis example, right? We can specify a prior and a likelihood, meaning that without any other information, right? Without any observation, like at day one, you play tennis, and day two, just stay at home, right? If I can specify the prior, whether I'm going to play tennis or not, right? So I give the concrete model for the prior model, or for the prior, right? So here we just use a table. So we specify the prior probability you play tennis is 0.3, you're not play tennis and staying home is 0.7. Right? So this is one instance of the prior model. Right? So now let us look at the likelihood model. So likelihood means that we have to consider for any possible label choice, what is the likelihood of the feature vectors, right? So here, for tennis example, we actually have two possible labels, right? Play or not play, right? So that means we need to specify the probabilities that given you play, what is the likelihood of each feature vector, and given you are not playing, what is the likelihood of each feature vector, right? We actually need to specify two sets of parameters for likelihood, right? So if you look at the example here, right, we actually have two likelihood models. One likelihood model tells us that given the label is yes, meaning that you're going to play tennis, right? What is the likelihood of these two features? Like suppose we're just dealing with two features, like temperature and wind. That means for every combination of temperature and wind, we have to assign a probability, right? So here we give like, given you're playing tennis, then your temperature and wind are hot and strong respectively will be 0.15, right? And the probability that your temperature is hot and wind is weak is 0.4, and so on. Right? And I also need to specify, given the label is negative, meaning you don't play tennis, right? You just stay at home, what is the probability or likelihood of each possible values of temperature and wind, right? So you have a different set of likelihoods. So once we specify those parameters, meaning prior and the likelihood under each possible label, then we can use it to make a prediction, right? For example, now I see today's weather has like hot temperature and has weak wind, right? I want to use my model to predict whether I should play tennis or stay at home, right? Following the framework we just mentioned, right? We want to maximize the joint probability, meaning that we want to maximize the prior of playing tennis, multiplying the likelihood given your choice. What is your likelihood of your observed temperature and wind, right? So we just use those model parameters to calculate, right? If your play decision is yes, right, meaning that label is yes, then the joint probability will be the prior of playing, which is 0.3 times given you're playing, meaning that label is yes, then what is the likelihood of hot temperature and weak wind, right? And what we need to do is just look at this table, right? Because this models the likelihood of every possible feature values given yes, right? So our observation is that hot temperature and weak wind, which is here, right? Second line. So this likelihood should be 0.4. So you multiply likelihood with the prior probability, you get your joint probability 0.12. Right? And similarly, we need to compute if you choose another label, what is the joint probability, right? If you choose another label, which is negative, you don't play, right? And the prior will be 0.7, is here, right? And what's the likelihood? Can anyone tell me what's the likelihood? Yeah, you should look at second table, right? That tells that given your label is no, what is the likelihood of every possible feature values, right? So our feature values are temperature hot and wind weak, which is also the second row, right? So the likelihood is 0.1. So multiply the likelihood with the prior, you give the joint probability, which is 0.07. Right? Now, which label should we predict? Which label should we predict? Yes, right? Why? Yeah, it has a larger joint probability, right? Remember our prediction rule is that, okay, we're going to maximize the joint probability, right? We're going to pick up the label who gives the largest joint probability. Of course, it's yes, right? So I should predict yes, meaning that I should go out and play tennis. Map prediction is yes, right? Okay. So I have a question about this instance, this example. Hopefully it gives us a concrete sense about how we're going to execute our prediction under this Bayesian model, right? Okay, next. How should we train this model, right? So know that, okay, we know once we specify those model parameters, which decides what's the prior, what's the likelihood given all kinds of possible labels, right? We need to consider, right, given the data, are you able to efficiently learn those parameters out of data, right? So to this end, right, we want to look at in more detail from this playing tennis example, right? To say how hard for us to learn this probabilistic model, right? So we're gonna look at the whole tennis playing data set. We know that we have 14 pieces of records, right? 14 records, and we have 4 features: outlook, temperature, humidity, and wind, right? And each feature takes several different values. Like outlook can take sunny overcast rain, SOR, as abbreviated, right? Temperature hot, medium, cool, humidity high, normal, low, wind, strong, weak. Like suppose we want to build up a probabilistic model, as we just mentioned, right? Over this data set, again, we need to learn 2 sets of parameters, right? One set of parameters determine the prior probability, whether I'm gonna play or not, right? Without any observation, right? And the second set of parameters decide the likelihood models, right? Given play, what is the possible likelihood? What is likelihood for every possible choices values of these 4 features, right? And given you're not playing, the labels know what is the likelihood of all possible feature values combination, right? So let us look at the 2 components one by one, right? The first one is the prior component. So if you want to decide the prior probability of you playing or not, how many parameters do we need? Any thought? Yeah, but we need but how many parameters do we need to specify this probability? Yes, that's the key, right? That's something I want everyone to realize, right? So although we have like 2 choices, we can decide to play or not to play, right? But as long as you know one probability, you know the other. Why? Because the summation is 1, right? Your probability, right? Your probability distribution over you play or not play, it should be 1, right? So once you know one probability, you got to know the other probability, but subtract it 1 by that probability, right? Does it make sense? Right. So then, looks like finding a single parameter for the prior model seems reasonable, right? Seems effortlessly, right? But what about our likelihood, right? So likelihood model should decide that for every possible label choice, what's the likelihood for every possible combination values of the X, right? So we got 4 features in total. And each feature can take 2 or 3 values, right? And we need a value for every possible assignment for the feature combination, right? So let us count, right? We need, for the all-look feature, we got 3 possible values, right? For the temperature feature, we got 3 possible values. Humidity feature, we got 3 possible values. For the wind feature, we got 2 possible feature values, right? So how many combinations do we have? 3 times 3 times 3 times 2, right? So that means for this many, let me just count. It's 54, right? It's 54 possible values of this feature vector. For every so every possible configuration of this 54 possibilities, you have to assign a likelihood, a probability, right? So pretty many, right? So you only have 14 training examples. But even for one likelihood, meaning that given one possible label, you have to assign 54 minus 1 probability parameters in that case. It's a little bit over, right? So now I want to check like why we only need 54 minus 1 rather than 54 parameters. Yes. Yes, exactly, right? So this is actually, if you look back our order, the conditional probability, right? Given this label, then the summation of the probabilities of possible choices of X should be 1, right? This is just the probability distribution over all combinations of X values, right? So that means if you have 100 possible values for X, right? You only need 99 probabilities, right? And the remaining probability is just 1 subtracted by the summation of these 99 probabilities, right? That's why for, in this case, right, we have 54 possible value combinations for the four features, right? And to parameterize the likelihood, we only need 54 minus 1, which is 53 parameters. Because the remaining probability, which corresponds to whichever combination, you can just calculate by subtracting 1 from summation of the remaining from the other 53 probabilities. Okay. And this is just for one label, right? You got to know what is the likelihood given you're not playing, right? You have to another 53 parameters to decide that likelihood model. So you can imagine, actually, the number of parameters is much larger than the number of training examples. So that might be troublesome, right? Now let's extend this problem. Let us look at, in the general sense, should we be okay to learn such a model? So in the general case, like suppose I got k labels, right? That means my prediction could be multi-class prediction. I could predict the outcome as label 1, 2, 4 until k, right? Then to decide the prior probability, right, we need k minus 1 parameters, right? Because the summation of the prior probabilities over every label is 1, right? You only need k minus 1 parameter. The remaining one is just subtract 1 by the summation of this k minus 1 probabilities. Then what about the likelihood, right? And suppose now you got D features, right? And here for simplicity, let us assume every feature is just a Boolean feature. Okay. Now to specify one likelihood, meaning that given one possible choice of label, say label small k, right? How many parameters do we need to decide this likelihood model? Right? If you happen to say this number, right, just give me an explanation. Yes, exactly, right? So let me rephrase, right? So again, now we have D features, right? Given any particular label choice, right? We need to decide what's the probability for every possible combination of these D features, right? So how many combinations of these D features do we have? Each feature can take 2 possible values, right? It is a Boolean feature. We got D features in total. How many possible combinations of those feature values? Yeah, 2 to the D, right? The first feature can take 2 values, second feature can take 2 values, third feature can take 2 values. We got D features. So overall, we have 2 to the power of D possible combinations of those D features, right? And for every combination, you have to assign a probability, right? Does it make sense? Okay. So that means for this particular likelihood, we're going to have a 2 to the D minus 1 parameters. And we have K labels. So I have to specify K such a likelihood. So that's the total number of parameters to decide likelihood model. You got a question? Yeah, K is just a number of possible labels. So any question? Does it make sense? Right. Let me repeat. Right. So for the likelihood model, given any specified any specific choice of the label Y, right, you have to determine what is the probability for any combination of these D features, right? And there are total 2 to the D combinations of these D features. Why? Because each feature is a Boolean feature, can take 2 values, right? So x1 can take 2 values, x2 can take 2 values, until xd can take 2 values, right? So there will be in total 2 to the D combinations of those values, right? And then for each specific combination, say x1 is 1, x2 is 0, x3 is 1, and so on. You have to specify a probability, right? There are 2 to the d such combinations. So the number of probabilities we need is 2 to the d minus 1, right? As to why we do not need 2 to the d, because their summation is just 1, right? So you just need 2 to the d minus 1 probabilities. Right? Does it make sense? Right. Okay. So from the number of parameters we analyzed, right, in the general case, what can we see? What's the problem can we see? Yeah. What kind of severe issue will happen in training? Hmm? Yeah, that's the issue, right? You cannot collect the data in exponential speed, right? But your model parameters grows exponentially along with the number of features, right? That's that's horrible, right? So imagine that you got 100 features. Right? You got 100 features, then the number of parameters you need is more than the number of the atoms in the universe, right? In the whole universe, right? And I guess you can at least you can at most collect like 1 billion training examples, right? But it's still far worse. It's far less than the number of parameters required. So that's an issue, right? It needs too much data to estimate so many parameters, right? And the consequence that in a relatively moderate size of the model, right, you won't be able to find sufficient data. And then you either lack of data or you kind of overfit data, right? Does it make sense? So that just tells us, right? This just the analysis tells us that you can't just design a model in this way, right? Because it brings too many parameters, right? It's not feasible to estimate in practice. And how can we address this problem? As we just said, right? This naive or this straightforward modeling will introduce high model complexity and easy to overfit, right? And how can we deal with this? Any thought? Yeah, I think you're thinking the right way, like, in the same direction I want to discuss, right? But here, as we look into this problem, the exponential growth of model parameters comes from the model structure, right? We actually assume this model structure is so flexible. It covers because it can describe every possible combinations of x1 to xd, right? Without any assumption, right? So that is overly complicated. That is overly expressive, right? So to reduce the model complexity, we're gonna simplify the model structure. We're not trying to let our model fit to any possible situations. We're gonna put in more strict, more simplified assumption over the model structure. So what kind of assumption should we impose to simplify the model structure? Right? Here we're going to use the independence assumptions. So what that mean for independence assumption? We're going to assume that given the label, the joint likelihood or joint probability of these D features actually can be decomposed as the individual likelihood of every feature. In other words, condition on the label, the features are independent to each other. That's our assumption. Of course, you can specify other structures. Like here, we just use the example from USB naive Bayes as an example to illustrate this idea, right? Okay, so let us recall conditional independence, right? So what is conditional independence? Suppose we have x, y, and z, three random variables, right? We say as x is conditionally independent of y given z, if the probability distribution of x is independent of the value y when z is observed. So if we write it down as a formula, it is like this. So condition on z, the joint distribution of xy is equal to the product of the conditional distribution of x given z and conditional distribution of y given z. Of course, you can write it in this way. That is condition on z and y. The x's probability is the same as the condition of z only. Right? It's actually the same definition. So now let us say if we apply this conditional independence assumption over the likelihood model, what will happen? Right? As we just discussed, if we just model the whole likelihood, that is the d features given the label y, right? It requires k to the power of 2k times 2 to the d minus 1 parameters, right? Because for every possible label y, you have to specify the probability for every possible combination of these d features. So we got 2 to the power of d combinations, right? So that's end up with this many parameters, right? But now, if we impose the conditional independent assumption, right, which is also called naive Bayes class assumption, then the joint distribution over the d features condition on y can be decomposed as the product of each feature value given y, right? So p of x1 given y, p of x2 given y, until p of xd given y, right? Now, to decide each individual likelihood, how many parameters do we need? Just one, right? Because each feature is binary, right? So if you want to decide what is the probability x takes 1 given y, or takes 0 given y, it just need one, right? Because once you know the probability x1 is 1, then probability x1 is 0 is 1 subtracted by the probability x1 is 1, right? So we got d such likelihoods, right? So we're gonna only have a d features. We only need the d parameters to decide the likelihood given a particular label, right? And we have k possible labels. So in total, we're gonna have kd parameters overall, right? It's not too bad. Now the model parameters is just linear in the number of features, right? It's no longer exponential to the number of features. So you have you obtain a great simplification of the model structure, which dramatically reduce the number of model parameters you need. Does it make sense? Right? And this model assumption is called naive Bayes assumption, and this model structure is called naive Bayes. Any questions so far? Okay, great. So now we come to our naive Bayes classifier, the kind of more detailed formulation, right? So the key assumption taken by naive Bayes is that features are conditionally independent given the label one, right? Once we have the prior probabilities and likelihood probabilities given each label for every feature, right? If we want to make a prediction, right, we follow the previous framework.
we're going to maximize the joint probability, which is prior multiplying with likelihood, right? And the likelihood, according to the naive Bayes assumption, can be further decomposed as likelihood over each individual feature, right? So eventually, our prediction is to maximize the prior multiplying the likelihood of every feature conditional on the condition on the label. So that's our naive Bayes classifier. Any question before we proceed to the training?
So is there any, like, for this example, you say turning like all of our features into line features, does that have any impact on the classifier? Or is it the same as if you just have them more
That's a good question. Actually, you can convert it into binary, or you can just stick to the original feature value. But in that case, you have to use different likelihood, right? Which here we use binary. We're assuming binary features just to give us a sense, like it's easier for analysis to show that, okay, how many training example, how many model parameters you will need for that case, right? And if you do this naive Bayes classification, how many parameters will be reduced, right? But in practice, you can choose whatever likelihood as long as it fits your feature value or feature type. Okay. Any other question? Okay, so now let us discuss how we're going to learn the naive Bayes classifier. Right. So in the naive Bayes classifier hypothesis space, right? Each hypothesis is defined by the is defined by a collection of probabilities, right? So it consists of the prior probability for every label and the likelihood for every feature given a label, right? So that's how we're going to define a hypothesis in the naive Bayes classifier's hypothesis space, right? And then we suppose we have collected a data set D, meaning m pairs of the feature vector and labels, right? And here, the bolded xi just means ith feature vector. And for notation convenience, we'll add additional subscript to x to index the feature, right? So xij just means the jth feature in ith example. So the first index in the subscript denotes which example, right? And the second index in the subscript describes the feature. Like xij means for the ith example, jth input feature. Okay. So then let us use maximal likelihood estimation to find out the model parameters, meaning that I want to find out a hypothesis. Right? Remember in our definition, right? The naive Bayes classifier's hypothesis space, each hypothesis is defined by a collection of parameters, including the prior probabilities and the likelihood probabilities for each single feature, right? So we're going to use a probabilistic criterion to find the hypothesis. As we described in the previous lectures, we got two criterion. One is based on maximum likelihood, the other is based on map estimation, right? So here we just look at the simple one, right? We want to use maximal likelihood estimation. That means we're going to search over the hypothesis space and find out a hypothesis H who gives the largest likelihood of the data, right? And here again, I just want to emphasize H is defined by all the probabilities used to construct naive Bayes decision. Right? So again, we're going to assume each example in dataset D are RID, meaning that this likelihood can be further decomposed as the product of individual likelihood for every example, xi, yi, right? So that means we're going to maximize the product of the likelihood for xi, yi given your hypothesis, right? And for each example, right, this likelihood can be decomposed as what is the prior for the label yi. And given label yi, of course, the H, hypothesis H, which contains all the parameters inside that, right? What is the likelihood of the feature vector xi, right? So here is where we inject our naive Bayes model. Like for the prior probability, we just take out the probability parameters inside H to determine the prior of yi, right? For the likelihood, we're gonna leverage our conditional independence assumption. That is, this likelihood is the product of the likelihood of every feature xij given yi, given your current naive Bayes model H. Okay. Again, xij is the jth feature of the ith example xi. Okay. And then our goal is to maximize this joint, maximize this this product over the probability of every training example. Okay. Any question? Okay. How do we proceed? As we mentioned, we're not going to deal with the product of many terms between 0 and 1, right? If you just multiply them together, sometimes at some stage you will incur numerical underflow, everything becomes 0, right? To be numerical stable, we usually take a logarithm, right? We take a logarithm over this joint probability, right? And take a logarithm of the product, you convert it into summation of log, right? So actually, just we need to do is maximize the summation over all the training examples. And inside, for each training example, we have this log prior of the label and the log conditional probability of each feature value given the label yi and the hypothesis, right? Remember, the hypothesis contains all the required model parameters here. Right? So what's next? Yes. Remember, this H is determined by the prior probabilities and the likelihood probabilities, right? You want to estimate those probabilities, right? Finding the right probabilities which maximize the whole likelihood, essentially to finding the right hypothesis H, right? So that means we can maximize this likelihood by taking a gradient, right? Using gradient-based optimization. So we need to make a model assumption about the function form of these probabilities. Okay. Otherwise, we don't know what kind of gradient can we compute, right? So first, for prior, right? We got the prior probability is 1 is P, and is 0 is 1 minus P, right? Then for the likelihood, for each feature given the label, we can denote the label as follows, right? We denote the conditional probability that the jth feature to be 1 given label 1 is AJ. And then the conditional probability of jth feature is 0 given label 1 is 1 minus AJ, right? And remember, we're having to also decide what is conditional probability for y is 0, right? So I have another parameter, right? The probability jth feature is 1 given y is 0 is BJ, denoted by BJ. Then the probability j's feature is 0 given y is 0 is 1 minus BJ, right? And remember, for every feature j, we need to specify AJ and BJ, right? So actually, we might have quite many AJs and BJs, right? And our hypothesis H consists of all AJs and BJs, also of P, right? So now to do the gradient, right? We need to compute the gradient of this likelihood term, the whole likelihood, with respect to the parameters, including B and all AJs, BJs. How can we do that? We need to specify this log likelihood as a function of P, AJs, and BJs. Right? To do that, we're gonna introduce a very common user trick. Right? Actually, for the prior probability, according to the parameter P, we can write down this probability in this form. So this bracket, this square bracket, is called the indicator function. Meaning that if yi in your data, right? Remember, yi is the ith label in your data, right? Is 1, then this indicator is 1. Otherwise, this indicator is 0. Right? In general, the indicator function is 1 only if the inside equation or other conditions are satisfied. Right? If yi is 0, then this indicator is 0, and this indicator is 1. Right? So we can represent the prior probability of your observed label yi in terms of this form. Right? It is satisfied no matter your observed y is 1 or 0. Right? Does it make sense? Right? And similarly, for the conditional likelihood, right, for every feature, right, we can write down this likelihood just in one function in terms of aj and bj. So see that this probability can be represented as aj to the power of an indicator times 1 minus aj to a power of indicator, bj to some indicator times 1 minus bj to the indicator. So each indicator just represents in which situation the probability should be the base, right? So we know that when the label is 1 and the feature takes 1, then the probability should be aj, right? So that's what the indicator says. And when label is 1, the feature is 0, then the probability should be 1 minus aj, right? And when label is 0, feature is 1, bj. Label 0, feature 0 is 1 minus bj, right? So it's just like a switch, right? Once the indicator is 1, meaning that switch is on, and you take the corresponding probability, right? And for all the other probabilities, because indicator 0, you know, the base to the 0 is simply 1. It doesn't affect anyone. So in this way, we can summarize the likelihood as one function in terms of the possible parameters aj and bj. Does it make sense? Any question? And then we can just substitute the function form of the prior and the function form of the likelihood into here, right? And once you take logarithm, you know that the indicator function will become the coefficient of the log p, or log 1 minus p. And similarly, when you take logarithm over this likelihood, all those indicators are put in front of the log, right? And you're doing log aj, log 1 minus aj, log bj, log 1 minus bj. Right? Then, because you're doing the logarithm of those parameters, right? The whole function is continuous, just take gradient with respect to p, aj's, and bj's. You set the gradient to be 0. Does it make sense? Right? We're not gonna go through the detail how you're gonna derive this because it's really calculus 1. Okay. So if we substitute our likelihood function and prior function into the whole objective and take the gradient, set the gradient to be 0 to find the parameters which maximize the whole training data likelihood, we'll get the following result. The optimal P, I mean the parameter P, it's just across the whole data set, the ratio of your positive label. Right? That is, you count positive label over the whole data set and divide it by the total number of examples in your data set. That is your optimal prior probability of P. Right? Now how do we calculate optimal AJ? Right? It's also very simple. You just count how many examples who are positive and the J's feature is 1. Remember, AJ just represents the conditional probability that your label is 1 and your J's feature is 1, right? And AJ, by our maximum MLE estimate, tells us the optimal AJ should be among all the positive examples, the ratio of examples whose J's feature is 1. Right? It's very intuitive, right? Similar, BJ is among all the negative examples, the ratio of the examples whose J's feature is 1. And that's it. So now let us look at, so actually this gives us a rule to find out the optimal parameters for naive Bayes, right? You don't need to do the substitution and gradient calculation derivative again, right? We can just use this rules to find a optimal parameters for naive Bayes classifier of any data set, right? Mm-hmm. Yeah, that's where I'm gonna see that. You want to see how we derive this?
No, I can.
Mm-hmm. Yeah. So it basically this form. I didn't say it explicitly. It's just Bernoulli likelihood, right? And this form, it's just two Bernoulli likelihood multiplied together, right? But here we should consider you have two possible labels, right? So multiply them together is totally fine. You have just add one more indicator, right? Right. So essentially, it is a maximize a Bernoulli likelihood. Right. So now let us try to apply the rules we have just derived on a concrete example to see how we get our naive Bayes classifier. We go back to our tennis playing example, right? We got 14 examples. So first we want to decide the prior parameters. Right? As we mentioned, we just need to know what is the prior probability to play tennis. And what we need to do is that, okay, we just count how many examples are positive, which are those yellow examples, right? We have 9 such examples. So then we get our probability. We get our optimal prior probability for naive Bayes classifier, which is 9 or 14, right? And then the parameter for the negative, for the probability for the negative example is for the negative prediction is 5 over 14, right? Just 1 subtracted 9 over 14, right? And then for the conditional, for the likelihood models, right? We can take a look at one by one, right? So first we'll take a look at the feature overcast, right? So we need to know, given positive label, what is the probability for overcast taking different features, right? So as we mentioned, right, what we need to do is that we just look at how many positive examples, because we're conditioning a positive label, right? The ratio of the overlook feature taken different values, right? So if you look at Sunny, we see that among all the positive examples, right, there are only 2 examples whose overlook feature is Sunny, right? And then we have 9 positive examples, right? So then we get our conditional probability of overlook take Sunny given positive label as 2 over 9, right? And similarly, the conditional probability for taking raining given positive label is 3 over 9, because among these 9 positive examples, we found that 3 examples are raining, right? So the ratio is 3 over 9, right? And similarly, you can compute the conditional probability that overlook takes overcast feature value given positive ratio, right? So again, you're going to look at among these 9 positive examples, how many examples have overcast, which are 4, right? So the probability is 4 over 9, right? It's just the counting, right? And similarly, you can compute the conditional probability for temperature taking high, middle, and cold, humidity, and wind, right? And similarly, you can compute what is the conditional probability given that your label is negative, the outlook takes sunny, raining, overcast, and so on. Right? In this way, you can directly obtain the optimal model parameters for naive Bayes classifier. Okay, so I want to ask a question. Right? So this is really simple, right? Really straightforward and intuitive. But what's the problem? There could be some devastating issue, disastrous issue that break down your whole model. Yeah, that's one issue, but that's not the primary issue. I know that, okay, those features are actually not independent, but you enforce them to be independent. I know there could be some misspecification here, right? But surprisingly, in practice, even you do this, naive Bayes works pretty well. Right? Mm-hmm. Yeah, exactly. So actually, I want to merge the points into one. So the critical issue is here. What if on some case your count is 0? Right? I know that if you, for example, if the overcast feature value only appear in negative examples, and in the positive examples the count is 0, and then you have one parameter to be 0, right? And if next time, like when you make a test, we'll do a test. You say your test feature input contains overcast, right? Then, for the positive label, your joint probability will simply 0, because 1 likelihood is 0. Of course, that's not that'll make your prediction meaningless, right? That will destroy your classifier. That's the key issue. And the major problem is that in practice, the data sparsity is not uncommon. It's very likely to happen, as long as, especially you have a lot of features, right? You might have 1,000 features. That's not uncommon, right? And you might have 200 examples and 300 examples. That won't guarantee that for every possible label, you're gonna see every possible feature value in that subset, right? Then you're gonna have many 0 estimate of the conditional probabilities, which break down your classifier when you make predictions, right? So that's an issue of you just train naive Bayes classifier following the maximal likelihood estimate principle. So now I want to ask, right? How are you gonna fix this issue? Any thought of fixing this issue? Or any guess? Threshold, okay, how do you want to threshold? Oh, okay, that's one one way to fix it, and very useful for practice, right? Like if I say there's no zero, there's no value, no observation on say positive examples, I'm not gonna set it to 0. I'm gonna set it to a small value. Let's say 0, 1, 0.1, or 0.01. Right? That's one way, right? But we want to give a more systematic view of how to fix that problem. Mm-hmm. When you don't know is divided by what? Uh-huh. Yeah, I got one. Yeah, this is a very good idea. I think I feel like it's even better than the solution I'm gonna tell you. Yeah, let me rephrase her idea. It's like you just look at throughout data, what kind of combinations you have not appeared, right? And you're gonna assign some probability, remaining probability over this unseen combinations. Probably you partition those probabilities into every possible unseen combination. And now once you see that, you just pick up that one as your probability. That's a very nice idea. But here I'm not gonna talk about that. That's a little bit more complicated than I want to offer. Can I say again? You want to use a one hot encoding to what? Uh-huh. I still didn't quite get a point. Are you saying like you're gonna encode some unseen things as a separate category? Yeah. Uh-huh. So yeah, if you using one hot encoding just to index labels, right? And I don't see, or I can't see right now, like how do you gonna use that to address the sparse observation issue, right? You can, I mean, my initial understanding about what you're saying is that, okay, I'm gonna use some one hot encoding to represent all the cases, all those holes where you didn't see any data, right? You assign some probability over that. And once you see that, okay, I'm gonna pick that probability to substitute 0, right? Yeah, this is actually, I mean, conceptually the same as what she proposed. Yeah, that's very nice. Yeah, but here I just want to give you a commonly used approach that we're gonna not using MLE, we're gonna use map estimation. Right. Map estimation means that okay, for those parameters, remember the probability, the prior probability of play or not play, the conditional probability of feature taking different values, right? All those parameters, if we denote by them theta, right? We're gonna assign some prior distribution over that, right? Then plus the likelihood of the data given theta, which is the solely objective we maximize, right? So if you're doing this all together, then your optimal estimate won't only be dependent on the data. There was some prior information here. And this prior information, something here, right? This prior information will avoid your optimal estimate to be 0 if you really lack of data. Does it make sense? Right? It's kind of conceptually same as what you just mentioned. Like, okay, if I don't observe any data, just assign some probability, right? But it can be explained as some prior distribution, the prior distribution over this probability. And if the count is 0, this probability is collapsed to the prior. Assign it, which might be 0.1 or 0.05. Right? That's one common use approach. And this also tells us that why doing regularized empirical risk minimization is important, because once your data is very sparse, you don't meet an awkward situation that break down and classify. Any question? Great. So now we have finished the introduction of naive Bayes. So to summarize, if we conduct learning of naive Bayes, and if we just doing the maximum likelihood estimation for the probabilistic criterion, then the learning is really straightforward, right? You just count how often features occur within each label and calculate ratio, right? And prior from the fraction of examples with each label. Then, and you can generalize to multi-classes, right? But as we just discussed, there can be some problem here, because if within some label that feature doesn't occur, your probability will become 0, right? And make your classification procedure malfunction. So that's why in practice, people won't directly use that. Like they usually will put some prior over those parameters. So your estimate, your optimal estimate of the parameters will be some correction over the count and ratio. And during the prediction, right, you're going to use those parameters to find the highest joint probability or log joint probability, and you find out you predict that label. Right? And naive Bayes classifier is very simple, but it's widely used for spam email detection. Right? It's very helpful, because how are you going to decide an email is a spam email, right? Email is you have a length, right? It consists of a lot of words, right? So naive Bayes classifier is usually like treating a feature as a word, right? And then if this word appears or not, so it's a binary feature, right? So the train classifier, they will like conditional the label. This word appears and that word appears are independent, and then the train model to make prediction. So you can see that this actually breaks assumption, right? You cannot assume in a paraphrase like 2 words are conditionally independent, right? They're not independent. But even you use this oversimplified assumption, in practice works pretty well. Okay, so let's stop here today and see you on Thursday.